Good morning, students, and welcome to today's session. So we will continue with heat and thermodynamics today. So we had discussed about thermal expansion the last time. Now, one last thing we will discuss in thermal expansion, couple of last things. One is the variation of density of a material with respect to temperature. Now, we know that density is equal to mass upon volume, or it is mass per unit volume. Generally, we denote density with the symbol rho. So since volume expands with temperature rise, and obviously mass remains constant, density decreases with temperature rise. So the formula becomes like this, that suppose at a temperature of T naught, volume is V naught. So density being rho naught is this much. Okay. Now at a temperature of T naught plus delta T, volume will become V naught into 1 plus gamma delta T. Okay. So what about density? That will become like this. Or we can say that density to the power minus 1. Okay. Now when we compare this with the first equation, you can see that this is rho naught into 1 plus gamma delta T to the power minus 1. And since gamma delta T is very small compared to 1, so we can bring the power inside binomial approximation. So this becomes 1 minus gamma delta T. This we are using the binomial approximation. One plus x to the power n is approximately 1 plus nx if x is small compared to 1. Therefore, 1 plus x to the power minus 1 becomes approximately 1 minus x. Okay. So this is the formula then for the variation of density with temperature. Yeah, we're just using this simple definition of density, that density is mass per unit volume. So mass divided by volume. Okay. So if at the original temperature of T naught, the density is given by this relation, at the new temperature of T naught plus delta T, it will be the same mass but divided by the new volume. Okay, that's all. is from the formula of volume expansion survey, which we've been discussing the last 2 lectures about thermal expansion. So volumetric expansion we have already discussed using coefficient of volume expansion. Okay, so let us look at an example. Suppose a certain liquid placed in a container has a volume of 500 milliliters at a temperature of 5 degrees C. Now, at a temperature of 65 degrees C, its volume has expanded by 0.25%. So first of all, find the fluid's coefficient of volume expansion. Secondly, find the percentage change in its density. And third, if the mass of the fluid is 750 grams, then find its density. Okay, just try this question out. immediate is 6 tau. Okay, anybody else got the answer? And Varun, what about the percentage change in the density? See, here we'll use the fact that at a temperature of 5 degrees C, the volume is 500 milliliters. At a temperature of 65 degrees C, which is 5 plus 60, the volume becomes this much. It increases by 25%. Okay. So the change in volume is 0.25% of 500 milliliters. So it is 0.25 upon 100. So this is our delta V. So that means delta V by V is 0.25 by 100 or this much. Okay. So this is what this means. Okay. 0.25% expansion in volume. That actually means this, that the fractional change in volume is 2.5 into 10 raised power minus 3. Now we know that the fractional is nothing but gamma into delta T. So from that we will get the gamma of the fluid. Okay, the change in temperature is 60 degrees C. So delta T is so this is the coefficient of volumetric expansion. Okay, so hope the calculation of gamma is clear to all of you. Now to find the percentage change in density, it's very easy. So we know that density is like this, okay, because density is mass upon volume. So now we know that gamma delta T is that much, no? 2.5 into 10 raised power minus 3. Therefore, the percentage change in density will be this much. So that will just be minus gamma delta T. So that will be a minus 0.25% change. So the percentage change in gamma, because see, volume expands according to this principle. So delta V by V is gamma delta T. Density changes by this principle. So this is minus gamma delta T. So if the volume has expanded by 0.25%, the density must have decreased by 0.25%. So there's no calculation required for this. Okay, it's the same percentage change, but it's opposite in sign. So when the volume expands, the density decreases. Okay. Now the mass of the fluid is given to us as 750 grams, and the density is 500 milliliters. And the volume is 500 milliliters at temperature equal to 5 degrees C. So at this temperature, so it is 1.5 gram per centimeter cube, because 500 milliliters is the same thing as 500 centimeter cube. So 1 ml, same thing as 1 cc. So density is generally expressed in gram per cc or kg per meter cube. So you can also write this as so at T equal to T naught plus delta T, which is 65 degrees C, density will become rho naught into 1 minus gamma delta T. Okay, so hope you understood the calculation here. Okay, just a minute. Yes, exactly. Because it is expanded by 0.25% surveys, so the density decreases by 0.25% at 65 degrees C. So this we've already done the calculation that the value of gamma delta T is 2.5 into 10 raised power minus 3. So we're just substituting the value. No, delta V by V is 25%. It's not delta V beta. 20, see, 0.25% change in volume. This what does it mean? It means that change in volume upon original volume converted into a percentage, that is 0.25%. Okay, this is what the meaning of this is. Percentage change of any quantity is fractional change multiplied by 100. Okay, so hope this is done now. So that is about thermal expansion. Now we move to the next chapter of heat and thermodynamics, which is called calorimetry. So calorimetry is about the relation between temperature and heat exchange, okay, or state change and heat exchange. So by state change, we mean, for example, liquid to vapor or solid to liquid, which is called melting. called boiling, etc. Okay. So this chapter calorimetry is about that. Okay. It comes from the word calorie, which is an alternate unit of heat. Okay. SI unit of heat, is joule. Okay. So 1 calorie is equal to 4.18 joules. So this is called the mechanical equivalent of heat. Okay, so the first mathematical relation we'll see here is that if heat is being supplied to any body or material, it can be a solid, it can be liquid, or it can be gas. Then its temperature rises such that delta T, that is the change in temperature, is proportionate to Q, that is the heat supplied, unless there is a state change occurring. So the temperature change is directly proportional to the heat supplied. Okay. Whereas during state change, the temperature remains constant until the state change has taken place completely. So we'll understand this with an example or two. Just make a note of this first. Okay, so let us understand this statement by a graphical representation. So suppose we are measuring the temperature of a certain material with respect to the heat we are supplying. So on the x-axis we have Q, which is heat supplied to it, okay, in joules or calories or whatever. On the y-axis we are measuring the temperature. And at the beginning of our experiment, we have solid material at an initial temperature of some T naught or whatever. Okay. So as we supply heat to the solid, what will happen is that its temperature will proportionately increase to the amount of heat that we are supplying, till it reaches something called, it reaches a temperature which is called the melting point. So suppose this is a solid material So you can see that for the solid, okay, for the solid, temperature rises from the initial temperature, whatever it was T naught, to a temperature which is called the melting point. With heat supplied being directly proportional to temperature change. Okay. Now, when we reach the melting point, what happens is that the solid takes up heat to melt, but while it is melting, there is no temperature change occurring. So it takes up a certain amount of heat for the melting process to complete. And during that melting process, temperature is not rising. Heat supplied is going into melting the solid. Now, once that melting process is complete, we have got liquid, and then again the liquid's temperature will rise with further heat supplied. Okay, so you can see that during melting, okay, at the temperature equal to the melting point, heat supplied results in state change, that is solid to liquid. Okay, and there is no temperature change until 100% melting has occurred. Okay, that is solid has completely converted to liquid. Okay, now once next what we see is once melting process is complete, okay, at temperature equal to the melting point, if further heat is supplied, then the liquid's temperature rises such that again temperature rise is directly proportional to the heat supply. Okay, then we reach a stage which is called the boiling point. After supplying a certain amount of heat, we reach a new temperature which is called the boiling point, where again there is a state change occurring. And once this state change is over, then again the gaseous state okay, then so again at a certain temperature called the boiling point, state change occurs. Okay. So just make a note of this portion first. I will just maximize it a little and note it down systematically. Then we'll write the mathematical equations for these relations. So again, you can see that once the boiling process is completed, okay, or it's also called vaporization. If further heat is supplied, then the gaseous temperature again rises proportionately. Okay, so now let us understand two new definitions: heat capacity and specific heat capacity. Okay, so we've already seen that for a material, whether it is in solid state, liquid state, or gaseous state, okay, when state change is not taking place, when state change is not occurring, the heat supplied is directly proportional to the temperature change. So this becomes the constant of proportionality here is called the heat capacity. Okay, so C is heat supplied per unit change in temperature for the given body or material. Yeah, Anshuman, let me finish discussing this part, then I'll go back. Okay. So, for example, we have, let us say, a metallic sphere such that its temperature rises by, let's say, 12 degrees C when 72 joules of heat is supplied. So, we want to find its heat capacity. So, C will become Q by delta T, or 72 joules divided by 12 degrees C, 6 joules per degree C. So that will become the heat capacity. So just make a note of this first, then we'll discuss the concept of specific heat capacity next. Okay, next up, let's understand about specific heat capacity. So in this equation that we have, Q is equal to C delta T, where C is the heat capacity. Now further, the heat capacity C, this is directly proportional to mass of the body into a certain property of its material called specific heat capacity, where M is the mass of the body or whatever material we have. Okay. And S is called specific heat capacity, okay, which becomes a material property. Or another way to understand specific heat capacity, that this is ms delta T. So when we have this equation that Q is equal to mass into specific heat capacity into delta T, we understand the value of S better, that it is heat supplied per unit mass per degree change in temperature. So this gives us an alternate way of defining this quantity, specific heat capacity. Specific heat capacity that equals the heat supplied per unit mass per unit temperature change. Okay, and therefore specific heat capacity is SI unit is joules per kilogram Kelvin. Okay, this is the SI unit. But other units are joules per gram degree C, calories per gram degree C, etc. Any unit of heat divided by any unit of mass into temperature is an equivalent unit for specific heat capacity. Okay, so for example, specific heat capacity of water is 1 calorie per gram degree C, which is the same thing as 4.18 joules per gram degree C, or 4.18 joules per gram Kelvin, because the temperature change of 1 degree C is the same as the temperature change of 1 Kelvin. So that becomes 4180 joules per kilogram Kelvin. So this is in the SI unit. So suppose we want to find out the heat in joules to raise the temperature of 200 grams of water from 2 degrees C to 52 degrees C. So Q will just become ms delta T. So 200 grams, okay, multiplied with 4.18 joules per gram degree C, multiplied by a temperature change of this much. So this is the basic application of the formula Q is equal to ms delta T. Okay, people, so hope this is clear. Next up, we will understand the concept of latent heat. Okay, so this is the concept of heat exchange during state change. So first we will understand latent heat of fusion. So if m amount of mass of a solid at its melting point is melted completely into liquid, then heat supplied is given by this formula, where this is called the latent heat of fusion. So latent heat of fusion is heat per unit mass. This is heat per unit mass of state change. In this case, melting. So it is expressed in joules per kilogram or calories per gram or joules per gram or whatever. Okay. So for example, latent heat of fusion of ice is approximately 80 calories per gram. So that means to melt 1 gram of ice at 0 degrees C into water, we need to supply 80 calories of heat. So let's look at a quick example. Now let's say two kilojoules of heat is supplied to an ice block of mass 10 kgs at 0 degrees C. So first of all, will all the ice melt? If not, then what percentage by mass melts to water? What percentage by mass of ice melts into water if all the ice is not going to melt? Just work this out quickly. Okay, very good, Ryle. You can see that we have a very small amount of heat compared to the amount of heat required to melt 10 kgs of ice. That's a lot more. Okay. So this 2 kilojoules of heat that we have, that is 2 into 10 raised power 3 joules. Okay. So if this melts, this is used to melt, let's say m mass of ice, then Q is equal to m into latent heat of ice. So 2 into 10 raised power 3 joules is equal to m multiplied with 80 into 4.18, okay, joules per gram. So m will become 2 kilojoules divided by 80 into 4.18 in grams, or in kgs. So that's a very small amount of ice, as you can see. So only about 6 grams, approximately 6 grams. So the answer to the first part is that no, only 6 grams approximately of ice melts. So the percentage melted will be 6 grams divided by the total mass converted to a percentage. So 0.6% melts. Yes, 0.056. Okay, so hope this is clear. Now we come to the main calculation part in this chapter, principle of calorimetry. Okay. So the principle of calorimetry is that if two materials or bodies at different temperatures come in contact, then heat exchange takes place until thermodynamic equilibrium is established. Okay, so thermodynamic equilibrium means equal temperature. Okay, such that the heat lost by the material or body cooling down equals to the heat gained by the material or body heating up. No, Sarvesh, we didn't find latent heat of fusion. I had given you the value of latent heat of fusion of ice, ना? ये पहले दिया हुआ था ना? This value we had written down, ना? Yeah. Anyway, let's come back to this principle of calorimetry. So this becomes the important equation for us, okay? That heat lost is equal to heat gained. So let's look at an example of this. Okay. So you have to find the final equilibrium temperature. Here when we say equilibrium, we mean thermal equilibrium, not mechanical equilibrium. Okay. So obviously the material which is cooling down will be water, and the material which will be absorbing the heat will be equal to the ice, will be the ice. So we have to just use the principle of calorimetry, that the heat lost by the water in cooling down must be equal to the heat absorbed by ice to first melt, and then it might even heat up from 0 degrees C. Okay, so let's understand this question. Okay, so I'll verify your calculation. So first of all, see, we have 20-gram block of ice at 0 degrees C. Okay, so the heat absorbed to melt the ice block, let's say that is Q1. So that is equal to M into L. So that is 20 into 80. So 1600 calories of heat. Okay. Now suppose the final temperature is some X degrees C. So next, the heat absorbed by the melted ice to rise in temperature from 0 to X degrees C. Let's say that is Q2. So that will become M into S of water into temperature change. So that will be 20 grams into 1 calorie per gram degree C into X. So 20X calories. Okay. So assuming that the final temperature is X, the total heat absorbed by ice will be the heat to melt plus the heat to raise the temperature. So 1000 plus 1600 plus 20x calories. Okay. Now on the other hand, we have 800 milliliters of water at 30 degrees C. No, no. अरे ये आइस जो मेल्ट कर रहा है उसका है, not the water. Okay. Now 800 milliliters. That's the same thing as 800 cubic centimeters. So that's the same thing as 800 grams. Okay, because 1 milliliter is equal to 1 cc, and density of water we just saw is 1 gram per cc. So 800 grams of water at 30 degrees C. Now suppose this cools down to final temperature of X degrees C. So the heat lost this will be in calories. Okay. So now we bring in the principle of calorimetry. So the heat absorbed must be equal to the heat lost. So the heat absorbed is the heat absorbed to melt the ice plus the heat absorbed to raise the temperature from 0 to X. This must be equal to the heat. Okay. So we can see that 1600 plus 20x is 24,000 minus 800x. So 820x is 24,000 minus 1600. So that is 23,400. So X, the final temperature, so this will become 2340 divided by 82. So it will be about 28.53 degrees C. So final temperature Yeah, sorry. Okay. So the heat absorbed by the ice is the heat absorbed to melt plus the heat absorbed to raise the temperature from 0 to X. So the total heat absorbed is this much. And on the other hand, the heat that is supplied by the water, which is at 30 degrees C, is this much. So the two must be equated. Now, X is not the change in temperature. The change in temperature, see, the final temperature is X, na beta. So the change in temperature for the water initially at 30 degrees C, that is equal to 30 minus X. Whereas here the change in temperature, here delta T is X minus 0. हाँ तो सर्वेश वही तो कैलकुलेट किया ना, Q1 is latent heat m into L. So 20 grams of ice into 80 calories per gram. What is this? Is that only? Okay, so hope this is clear to all of you people. So that's it for today's session. Okay. Next time we will start with the discussion of kinetic theory of gases after doing some more problems in calorimetry. Okay, but this is all there is to this section of calorimetry: the definition of latent heats and the definition of specific heat capacity, and the application of the principle of calorimetry, that in heat exchange, the heat lost by one material is equal to the heat absorbed by the other material. Okay. No, thermodynamics is not over, beta. Kinetic theory of gases and first law of thermodynamics, that's the next thing. Calorimetry is over. Okay. If you see your module, you will see the list of topics in it. Once in a while, you should go through the module at least, na? So you have some idea. Anyway, so that's it for today's session. People, wish you all the best.